This is the GMAT 41. You are welcome to our General Physical Chemistry class. In this video, we start this course with the kinetic theory of ideal gases. Because you know that a gas can either be a real gas or an ideal gas. We're still going to look at the difference between real and ideal gases. We focus on the theory postulated in the 1860s by two scientists, James Clerk Maxwell and Ludwig Edward Boltzmann. They postulated this kinetic theory of ideal gases based on assumptions. And this theory we summarize here. We have them on the board. One of them is that gases consist of large number of tiny particles which we call molecules. So once you see a gas system, you want to know that this gas system is made up of molecules, many of them. Number two, gas molecules are in a state of constant random motion. They keep moving, alright? They don't rest, and they move along a straight path. They continue to move. They can only change their direction if they collide with another gas molecule or if they collide with the walls of their containing vessel. Just imagine that you have this as a gas and then it's moving this way. It will continue to move that way along that straight path. It can only change direction if perhaps it collides with another gas. Say there is a gas there. Once it hits it, it will now change its path. That is the concept of the random motion of gases. Otherwise, its motion is along straight path. Postulate number three, the pressure of a gas molecule is as a result of collision. When the gas molecules collide with the walls of their containing vessel, then the pressure develops. Of course, that makes sense. You know, these gases, they move with certain force. They have their own forces. So as the gas molecules move with these forces, they collide with the walls of their containing vessel. This vessel has area. Going by what Pascal stated, force divided by area would give us pressure. So we expect that colliding with the walls of their containing vessel will develop the pressure of gas molecules. The fourth one is that during collision there is no loss or gain in kinetic energy. That simply means that the kinetic energy before collision and the kinetic energy after collision are equal. Now, let's just think about this. What is likely responsible for the kinetic energy before and after collision being equal? That is only possible if the velocity before collision and the velocity after collision are equal. Of course, because kinetic energy we know is 1/2 mv squared. Where the v there is the velocity. And of course we know that velocity it's responsible, let's say kinetic energy varies with velocity. So if velocity does not change, it therefore means that the kinetic energy will not change. Please take note of this postulate number 4. We are going to encounter it as an assumption when we derive the kinetic gas equation, pressure of an ideal gas. Number 5, the average kinetic energy of gas molecule is dependent on the absolute temperature of the gas molecules. It has been found that this average kinetic energy is directly proportional to the absolute temperature of the gas molecules. Now look at number 6, there is no effect of gravity on the motion of gas molecules. So gas molecules are not affected by gravity. That's the assumption made. And number 7, the size of gas molecules are very small compared to their distance apart. So if you have a gas molecule, you have another one here. The size of these gas molecules is very, very small when you compare it to their distance apart. And of course, that is responsible for why their actual volume is negligible compared to the total volume of the gas. In the next video, we introduce the derivation of the kinetic gas equation of ideal gases. That is the pressure of an ideal gas. We now want to derive the pressure of an ideal gas, otherwise known as the kinetic gas equation. PV equal to 1/3 nmu squared. To achieve this, we consider a cube containing gas molecules. And this cube is such that the wall is perfectly elastic. We'll have the diagram here on the board. We've chosen to use space coordinates x, y, z, knowing that gas molecules move randomly in all directions. And so we're going to consider that a gas molecule moves from phase A towards phase B and then collide against phase B, rebounding back to where it came from, that is back to phase A. That's what we try to depict, to show on the board here. Each of the coordinates x, y, z has its corresponding velocities. Of course, we have the velocity in x direction, velocity in y direction, velocity in z direction. And we know that velocity is a vector quantity. And these three velocities are held at this point at 90 degrees. So we can actually get the resultant velocity using the knowledge of vector. That will make us to apply Pythagoras theorem. So the resultant vectors here is going to be, that is the resultant velocity of these velocity vectors. Alright, it's going to be u squared equal to ux squared plus uy squared plus uz squared. Remember, on the kinetic theory of gases, the postulate made by Maxwell and Boltzmann, the collision of gas molecules is perfectly elastic, so there is no loss or gain in kinetic energy. And you would recall that in the previous video I told you the implication. For there to be no loss or gain in kinetic energy, it simply means that the velocity before and after collision are equal. And in this case now we're going to assume that the velocity in all three directions are equal. Does that make sense, following that assumption under that postulate? Okay. Let us take small letter m to be mass of one molecule. U will be total velocity here, that's resultant velocity. Capital letter N will represent total number of molecules in our derivation. P will represent the pressure of the gas molecules as the total pressure, which is what we want to derive. We're going to take L to be the length of the cube, from phase A to phase B. The length is L. And I will wish to derive this formula. So to start with, we're going to consider a molecule, like I stated, moving from phase A to phase B along the x-axis. Is that okay? Now we're going to take a short break. When we come back from the short break, we'll start by determining the momentum of that gas molecule along x-axis before collision and the momentum after collision. Take note, we are using x-axis for our analysis. Whatever we're going to get from that x-axis will be the same for y-axis and for z-axis. All we need to do is just to replace the subscripts x with y or z as the case might be. That's going to be the basis of our derivation. Let us go for a short break. I will be back shortly. So you're welcome from the break. Having established the three-dimensional coordinate system of a gas molecule, we now want to see how we proceed in deriving the kinetic gas equation. Alright, so I still made another sketch here so we can be looking at this and then explaining what happens in the process. So are you ready for that? Remember, we have mass of one molecule of the gas moving from phase A of this cubical container, alright, moving to phase B, colliding with phase B and then rebouncing back to phase A. That's the condition upon which we are going to analyze this gas. Are you ready? Alright, follow me, let's do this. The first thing we want to obtain is the momentum of the gas as the gas molecule moves from phase A to phase B. Of course, we know that momentum is the product of mass and the velocity of the gas molecule. So taking this to be the gas molecule as it moves from phase A to phase B, then the momentum before colliding with phase B will be equal to mass times the velocity of the gas in the direction we are considering. Remember, we decided to pick the x coordinate to analyze, after which we generalize it for all the coordinates. So the momentum before collision will be given as the mass times the velocity in the positive x direction as the gas molecule goes towards phase B. What happens after colliding? It's just like playing a ping pong ball. As you play and hit possibly the wall, it rebounces back to you. Is that not so? Now, this gas molecule on colliding with phase B is going to rebound back with the same velocity with which it moved to phase B. Is that okay? So, what's going to happen? It's reversing its direction. So the velocity in that case is going to be negative. Remember, velocity is a vector quantity, so direction matters. If we take the movement in the positive x axis or direction to be positive, that is before collision, then after collision, when returning to phase B, we shall take the velocity as negative. And that gives us the momentum in the negative x direction, that is returning back to phase A now, to be equal to minus the mass of the gas molecule times the velocity of the gas molecule in the x-axis. Negative, take note. So having established momentum before collision and momentum after collision, we shall now get the change in momentum. The change in momentum. Because we know momentum is a vector quantity, and this is one-dimensional vector. Because the motion is linear, just along a straight line. Is that okay? Now how do we get the change in momentum? Of course, it's going to be the momentum before collision minus the momentum after collision. If you have two vectors, one moving this way and then the other coming this way, we're going to do the addition of the two by subtracting subtracting the two vectors to get the change. Now, that gives us that change in momentum is equal to MUX, that is momentum before collision, minus MUX, momentum after collision. This negative terms multiplies out to give us positive, and then you have mu subscript x plus mu subscript x. What does that tell us? That the momentum, change in the value of the momentum is going to give us 2 times mu subscript x. That's 2 times the mass of one molecule of this gas times the velocity in the direction it's moving. Of course, if the gas now moves from this phase A to phase B and then rebounds back, what is the total distance covered? The gas molecule will have covered a total distance of L plus L. Because if it takes the gas from here to this place equal to a distance of L, then coming back to that same place is going to be the same distance L. So total distance is going to be L plus L, which is 2L. This helps us to define the velocity of the gas. Velocity we know is distance over time. Of course, it's usually a concept of displacement, but you know, if it's a one-dimensional motion, you talk about the total distance divided by time, which is going to be 2L all over the time. Knowing that the total distance is equal to 2L. So we're going to divide it by time. And that gives us this equation 4. 2L is the total distance covered by the gas. Take note of that. Generally, we know the formula for speed, like, okay, distance over time. So it's meant to be simply L over T. But please take note that for gas molecule, after collision, the total distance covered is equal to 2 times one of its distance. Is that okay? Can we now define the number of impacts with the wall by the gas per second? What that means is simply to make time subject to the formula from equation 4. If we make time subject to the formula, we're going to get 2L all over the velocity of the gas. And that gives us the number of impacts with the wall by the gas molecule per second. In the next video, we are going to introduce Newton's second law of motion, where we define the rate of momentum in order to achieve the equation we are trying to derive. We now want to look at the rate of momentum, that is momentum per second of the gas molecule as the gas molecule collides with phase B and returns to phase A. To define this rate of momentum, we shall introduce Newton's second law of motion. Remember the equation that F is equal to what? ma. That's Newton's second law of motion. A there is acceleration, and we know that acceleration is the rate of velocity. That is velocity divided by what? Time. So if we eventually place velocity over time for acceleration here, mass times the velocity will give us what? The momentum. And take note, this acceleration is actually change in velocity. Final minus initial velocity, you know that. Which means if you open up, possibly if you write this as m bracket, final velocity minus initial velocity, close the bracket and divide by time. If the mass opens up the bracket, you're going to get mass times final velocity minus mass times initial velocity, which actually gives us the change in momentum. So actually, according to Newton, F equal to ma. This F equal to ma is still the same as change in momentum per unit time. So the rate of momentum of this gas is actually given as this equation 6 here, which is change in momentum of the gas along that x direction divided by what? The time. We are going to substitute equation 3 and 5 into this equation 6. And what is our equation 3? You would recall that we obtained equation 3 to be the value of the change in momentum, which is 2 times mass times the velocity of the gas in x direction. Change in momentum, we got it to be equal to 2mux. Is that okay? And then time, we obtain time to be the total distance covered after colliding with this B divided by what? The velocity in that x-axis. That being the case, if you substitute for this change in momentum and time, you're going to get this. If you work out this mathematically, you notice that this 2 will go with this 2, then this velocity will go upwards to multiply the numerator velocity, and that's going to give us mu subscript x squared. That is mu squared subscript x divided by what? L. That's the equation 7. So this equation 7 actually gives us the rate of momentum of this gas molecule. It's the same as the force with which the gas molecule collide with the phase, the phase B, and then rebounds. Now, at this point, having obtained equation 7, we now want to introduce the pressure of the gas now by dividing that equation 7 through by the area of this cube. So if you divide equation 7, the left hand side by the area, the right hand side by the area, we're going to get this. And then we know, according to Pascal, force divided by A, that is force over area, will give you pressure. So the force divided by the area, the force of these gases as they move in this box, divided by the area of impact, of collision, will generate the pressure of the gas. You would recall when we treated the kinetic theory of gases, we stated that the pressure is generated as a result of the gas molecules colliding with the walls of the containing vessel, knowing that this vessel has area. Good. Now this introduces pressure into the equation. This F sub x divided by area is the pressure in the x direction. That's the pressure of the mass of one molecule of this gas, because all our analysis up to this point is still based on mass of one molecule. That is now going to be equal to the mass times the square of the velocity in that direction, x direction, then divided by area times length. This A is area, this L is the length. Look at it, is the length. So area times length is going to give us what? Volume. So this V is volume. That V is volume. So having said that, you can now rewrite this equation that pressure in the x direction is equal to the mass of the gas times the square of the velocity divided by what? Volume. This is substituting. And that is how we arrive at equation 8. This equation 8 gives us the value of the pressure of the mass of one molecule in a given axis. If one can write this for y-axis as well, so all you need to do is to change the subscript x to subscript what? Y. And one can also write it for what? Z-axis. which of course you know will lead to get the total pressure in all dimensions. Now you add up all the pressures. Once again, we'll go for a short break. When we come back, we'll now see how we can translate the velocity in just this one direction to total what? Velocity, which will eventually give us the total pressure of this gas. That is the total pressure of the total molecule of the gas in this container. Before the break, we established equation 8. And that equation 8 is the pressure exerted by mass of one molecule in x direction. We obtained that pressure to be equal to the mass of one molecule, small letter m, times the square of the velocity in that axis being considered, divided by what? The volume of this box. Now, we actually analyze what happened to mass of one molecule, the pressure it generates just in x direction. The same pressure is generated in other directions, y and z. So we can actually write a similar equation for the y direction, that the pressure exerted by mass of one molecule in y direction is n u squared y divided by what? V. Where V is the volume, once again, of the containing vessel Q. Similarly, the pressure exerted by mass of one molecule in z direction will be equal to the mass of that one molecule times the square of the velocity in that z direction divided by the volume V of the cube of the containing vessel. Now our aim is to put all these pressures together in order to get the total pressure exerted by the total number of molecules in the gas system. Because we're just analyzing what mass of only one molecule can do. So what do we do from here? If we are able to rewrite the velocity in any direction in terms of the resultant velocity, in terms of the total velocity, then we can actually achieve the equation that we are looking for. How do we do this? We are going to quickly remember that the three velocities under considerations here, are orthogonal. Three of them are held at 90 degrees. Look at them. They are held at what? 90 degrees. Remember, these velocities are vectors. Now, on the basis of that, we can use Pythagoras' theorem to obtain the resultant velocity. And that's why we now have this equation that is square of the resultant velocity is equal to square of the velocity in x direction plus square of the velocity in y direction plus square of the velocity in z direction. When we discussed the molecular theory of gases, that's kinetic molecular theory of gases, we stated that the collision of gas molecules is perfectly elastic. Collision is what? Perfectly elastic. I recall explaining the meaning of that. That simply means that there is no gain or loss in kinetic energy. And by implication, where there is no gain or loss in kinetic energy, it simply means that the velocities are equal. That is, velocity before and after collision, they are equal. This assumption would allow us to say, okay, fine, let these velocities all be equal, but they are equal velocities. It therefore means that u subscript x will be equal to u subscript y, and it will also be equal to u subscript z. These three velocities are equal. That's the kinetic molecular theory assumption. If they are equal, let's choose to call all of them u subscript x, that is velocity in x direction. Therefore, this Pythagoras theory here will now become square of the resultant velocity equal to square of velocity in x-axis plus square of velocity in x-axis again, because this u subscript y is the same as velocity in x-axis, plus square of velocity in x-axis again, because of this assumption. Therefore, adding up this the same square of velocity in x-axis, you're going to get 3 times square of velocity in that x-axis. You're going to get this. Then making this square of velocity in x-axis subject of the formula, you divide through by its coefficient, which is 3. Therefore, the square of the velocity in any direction, be it x, be it y, or z, is actually equal to the resultant velocity square. That is square of the resultant velocity divided by what? 3. This equation 9 is very fundamental because it's going to now help us to get this pressure exerted by mass of one molecule. It's going to help us to get the total pressure now exerted by mass of one molecule in all directions. So what do? Simply come back to equation 8 and substitute equation 9 into it. Equation 8 is this already. So wherever we see the square of velocity in x-axis, we are going to put the square of the resultant velocity divided by 3. So if you substitute square of resultant velocity divided by 3 here, that will give us this equation 10. Equation 10 is the pressure exerted by a single gas molecule in all 3 directions, x, y, z. Pressure exerted by what? A single molecule, because we are still dealing with mass of one molecule here. Hence, how do we now get the total pressure exerted? If this is total pressure exerted by mass of one molecule in all directions, therefore, considering all the molecules where we refer to their number as what? Capital letter N, all we need to do is to multiply this equation 10 by that capital letter N. And if we multiply this equation 10 by capital letter N, we'll get this equation which I chose to call equation alpha star, because that's the equation we'll be looking for. That's going to be all these 10 times N, capital letter N, which can still be written as 1 over 3, total number of molecules times mass of one molecule times square of the resultant velocity divided by the volume of the bus. This capital letter N times mass is equal to the molecular weight of the gases. And this equation alpha star is the pressure of an ideal gas. Let me write that. We refer to it as kinetic gas equation, or simply as the pressure of an ideal gas. Good. So we are done with this. In the next video, we are going to see the deductions that can be made from this equation. What can we get from this equation? It might interest you that we can get things like the energy of translation of gas molecules. We can also get the Boltzmann's constant from this equation. We can also get the root mean square velocity of the gas molecules from this equation. That we shall make in the next video.